In this next section, we're going to talk about magnetism. So you've probably played with bar magnets before, or even just the refrigerator magnets. I know if I have a couple of refrigerator magnets, we distinguish between the ends of the magnets as a north end and a south end. If I have two magnets that the opposite poles, so a north pole and a south pole, if these poles, these opposite poles, are near each other, the magnets will attract. If we have two magnets and they have opposite poles near each other, similar poles near each other, they will repel. It can be fun to take a couple magnets and have the similar poles near each other and attempt to force them together. But we see that they repel. So we see a similar interaction as we did with charges, in that when we talked about electric force, like charges, so two positive charges repelled each other, or two negative charges repelled each other, but opposite charges, positive and negative, attracted. So this is similar in that way. What's different is that if I were to take a bar magnet, either pole, and I had it near some sort of charged object, whether this charge was positive or negative, there would be no interaction. Now, this is true as long as that charge nor the magnet, there's no motion. So there's no interaction if no motion of charge. It turns out that magnetism, though there's similarities to electricity, the magnetism in and of itself is not the same thing. So when we talk about the north pole or south pole of a magnet, these are not charged. So no net charge. It's really easy to want to kind of just assume one end is positive, one end is negative, but that's not the case. The magnet itself is neutral. And so we can't say there's a positive versus a negative charge. So magnetism is due to something different than just being charged, having a positive or negative charge. Now, when we talk about magnets, you may have had a magnet before and used it to pick up a paperclip or a nail. And it turns out, regardless of how I have the magnet oriented, my paperclip, that's my attempt at drawing a paperclip. A paperclip is attracted to the magnet regardless of which end of the magnet is closer. So the paperclip would be attracted to both a north pole and a south pole. Not all materials are attracted to magnets. Materials that are attracted to magnets they're called ferromagnetic materials. Materials that have iron in them oftentimes are attracted to magnets, and this prefix of ferro is iron, iron-like. So Many materials are not attracted to magnets. Which is sometimes surprising. It's very common to assume that conductors, because they conduct electricity very well, that all conductors are ferromagnetic, but that is not the case. For example, copper, aluminum, these are not ferromagnetic. So I cannot use a permanent magnet to pick up a piece of copper or a piece of aluminum. This is just a couple examples. Now, I want to show you a little video clip to see what we would represent, or how we would represent, what is called a magnetic field around a magnet. So similar to a charge, a point charge, in our last section, we were talking about electric field. And the electric field was a way of describing how this charge influenced the region of space around it, and in turn could exert a force on another nearby charge. So similarly, with magnets, we talk about what's called a magnetic field. And that magnetic field can exert a force on ferromagnetic materials or other magnets that also have a magnetic field. So in this video clip, this is just a piece of poster board, I think, and then he is going to sprinkle out iron filings, so little pieces of iron. Because iron is a ferromagnetic material, these iron filings will line up as if they're little tiny bar magnets themselves, like a compass needle, and they will line up with the magnetic field of the magnets that are underneath the board.
Okay, here we do. We've got a stack of magnets underneath, a stack of rock magnets, and we're going to put iron filings over the top here. And we finally got a piece of paper that's not glossy, so this ought to be easier to see. Alright, there's our magnetic field lines. As I tap it, they kind of align even better, especially on the outside. Things to notice. Which side is north and south? We can figure out with a compass. That south is attracted to a north, and north attracted to the south. Now, which one is which is really rather irrelevant. You'll notice in the center that they go straight across from north to south. Then they also go on the outside from north to south in these big arcs. Now with my hand, if I was doing the right-hand rule, magnetic field lines go outside of norths and into souths. Now what about here?
Okay, so we're going to be talking about some right-hand rules, which we don't really need to worry about with these magnets at the moment, but get this general idea. I'm going to draw a picture that somewhat represents this. The magnetic field, coming back to our screen, if I were to draw that lump of magnets, he had many magnets stacked together, which would be equivalent to just having one big magnet. So I'm going to draw it as one big magnet. The magnetic field lines, we saw this general looping of those iron filings around outside, but also we saw lines that just pointed straight between these poles. Now we used a little compass that was really quick. A compass needle is simply a very simple, tiny little bar magnet. A compass needle is a bar magnet. One end is north, one end is south. When we had to use the magnetic field of the Earth for navigation, compass needles were used. And this north end would always point towards the Earth's south pole, which happened to line up, or fairly closely line up, to Earth's north pole. I'll talk about that in just a minute. But compass needle, just a little bar magnet. When you placed it in this region, that little bar magnet lined up, pointing this way. So the North Pole is what he discovered was on the left end in his picture, which makes the right end the South Pole. So if you remember with electric field, we had to kind of just define a direction. So that is how it was chosen that the electric field would point away from positive charges, because we were talking about the direction of the force on a small probe charge or test charge. So that's kind of a definition as well with bar magnets and with magnetism in general, is based off of a compass needle, which would be our little probe. We find and define the magnetic field as coming out of north and looping around and going back into south. But this field continues inside south to north. So outside the magnet, the field points north to south. Inside, it points south to north. So something that is also different from electricity is these magnetic field lines are continuous. Magnetic field does not start or end anywhere. They are continuous. That's different than electricity as well. Okay, so magnetic field. The symbol we use to represent magnetic field is a capital B. And I'm not sure why. I don't recall if I learned. So magnetic field, we use capital B to represent it. Where the lines are closer together, it's stronger. Where the lines are farther apart, which we would see farther away from the magnet, it would be weaker. The units for magnetic field are Teslas. And we use a capital T to represent that. 1 full Tesla is an actually very strong magnetic field. Earth's magnetic field is around 50 microteslas. And so Earth, let me slide this, it turns out that Earth's magnetic field, so drawing Earth, the north geographic pole versus the south geographic pole, so Antarctica down here at the bottom. It turns out that Earth's magnetic field comes out down near the south pole of the Earth, but meaning the south geographic pole of the Earth, and comes in at near the Earth's north geographic pole. It's as if the Earth is a big old magnet with the north magnetic pole. So this N means magnetic pole. And then the south magnetic pole is closer up to the North Geographic Pole. And that's why these compass needles, the north would point towards North Geographic region. The Earth's magnetic field, though, is shifting with time, and it is not fully understood why. As far as what the current belief of the Earth having a magnetic field is due to the rotation of the Earth and the partially molten core. The reason why this is a current assumption or understanding, let me show you one other video clip. So this video clip, this wire coming out of this white background. So this white background is some type of paper or cardboard, I don't know, it doesn't matter, but it's a surface to hold these little tiny compass needles. And if you look closely at those compass needles, you'll see a little arrow on one side. So that's pointing in the north direction. So early 1800s, there was a professor, Ørsted, who had brought a demonstration to his class. Big battery. He was going to run current through that through some wires, and he happened to have a compass needle as well. I've heard this story as he was wanting to prove that electricity and magnetism were not related. I don't know what his actual intention was, but he had the equipment, both a battery with wires so that he could flow current, and then compass needle of some sort, and discovered that the compass needle responded to that flow of current. So we're going to see that as in this little clip. We won't watch it all, just part of it.
I have a wire that goes through a piece of cardboard here, and I've got it surrounded by little tiny compasses. They're all pointing generally this direction. I'm going to run current through the wire that will be coming up the wire this way from underneath. So based on the right-hand rule, there should be a magnetic field around this wire. In which direction? Let's find out. So I'm going to clip this on now. So it looks like all of the arrows are tending to go around in a counterclockwise fashion from this perspective. I'll turn the current back off. Now I'm going to reverse the current and run it the other direction. So in this case, the current will be flowing down the wire through the cardboard. And let's see what direction the field is there. And now they all seem to be pointing in a clockwise fashion around the wire. The farther I get from the wire, the weaker the field seems to get. I didn't quite line up as quickly or prominently. I'll pull them back a little farther. So they're all being influenced by the Earth's magnetic field there. They're not all pointing perpendicular to the wire anymore. They're being more greatly influenced by the Earth's field.
Okay, so they all are originally lined up in generally roughly the same direction because they are lining up with the Earth's magnetic field. But as soon as that current was created, so as soon as there was a battery connected and turned on, then those little compass needles all aligned in a direction that is tangent to a circle that would go around the wire. So if I come back to this screen here, that wire, when the current was flowing upwards through the wire, if we imagine this circle going around this wire, these little bar magnets lined up such that those compass needles, they lined up such that they would be tangent to that circle. If the current was flowing down, and we think about the similar circle, those little compass needles also lined up tangent, but in opposite direction. And he mentioned a right-hand rule, which we're going to talk about as well. But ultimately, this discovery, seeing that these compass needles aligned with a circle, so essentially the compass needle responded to the current that is flowing. We know that moving charges, it's the motion, the charges that are moving as current. So the moving charges, so the current, is what is creating, moving charges create magnetic fields. So when we talk about the Earth, as I mentioned before, that it is believed that it's the combination of the Earth's rotation and its molten core that is responsible for the Earth's magnetic field. Now, Earth's magnetic field's more complicated than that because physical geological evidence shows that the Earth's magnetic field has flip-flopped, has changed direction over time. As in, the North Magnetic Pole at one point in time was closer to the North Geographic Pole. And so that's not completely understood. So that is an active field of research. But fundamentally, moving charges create magnetic fields. So what is it about a bar magnet? A bar magnet doesn't have current flowing through it, right? Our bar magnet has a north and a south. It turns out if I were to cut my bar magnet in half so that I had two pieces, they would individually have north and south. So I cannot isolate a north pole from its south pole as far as magnets are concerned. In terms of permanent magnets, it is believed to be the spin of the electron. The spin, The spin of an electron is a fundamental characteristic of an electron describing some magnetic properties. We can think of it as an electron spinning, like an ice skater spinning, though on the true atomic scale, that's not what's happening. But there is a characteristic of electrons called spin. And if you take, I think it was in like physical chemistry, one of the chemistry classes, they talk about spin being up or down. It is that aspect of the electron that is related to its magnetic properties. In a material, any given material, little regions of the material will have different randomly oriented, what we call magnetic domains. This is talked about in the last section of your textbook, but it makes sense to bring it up right now. These magnetic domains are based off of the general spin of the electrons in that region. And in general, these magnetic domains are randomly oriented in a material, which is why most materials are not just magnetized, permanently magnetized to begin with. For materials that are ferromagnetic, meaning they can be magnetized. If I bring a magnet nearby this material, these domains will line up with the external magnetic field of the magnet. So the magnet's magnetic field comes out of north into south, loops around, and continues inside. And so these magnetic domains align. So they align with the external magnetic field. And capital B again is the symbol we're using for magnetic field. So notice inside this now material acts as if it's a north pole at the top and a south pole at the bottom. And thus we get this attraction. The opposite would be true if we had the north pole closer to the material. The domains would line up with that external magnetic field and create essentially the opposite pole in the closer end, and attraction would still occur. So that's why with paper clips or nails, you can pick them up with a magnet. It doesn't matter which side or end of the magnet you orient closer to them. So this chapter, we're going to be talking about magnetic field. We're going to talk about the magnetic field created around wires that are carrying current. We're going to talk about the magnetic field due to a moving charge, and then interactions between charges that are moving and external magnetic fields. And so we'll look at that in the upcoming videos.